All right, guys, welcome back. Here's the next video in our modern physics topics. Today's topic is talking a little bit about time dilation and simultaneity. So last week we kind of took a look at Galilean transformations and kind of introduced this whole concept of relativity. So we talked about how it came from electricity and magnetism. Talked about a nice, easy way, to describe how things are moving from different perspectives, from different frames of reference. And then we found out that it doesn't really work so well when objects are moving really fast, aka at the speed of light. As a matter of fact, of course, you would probably expect then, and a lot of you probably already know that the Galilean transformations also kind of start to weaken when objects are even moving close to the speed of light. And so now our goal today is to actually take that information and start to figure out, okay, well, how do objects actually work when they're moving near the speed of light then? The first thing that we're going to talk about, as the name of today's video suggests, is we're going to talk about how time transforms when things are moving really fast near the speed of light then. So a topic called time dilation. Before we get there though, just kind of a little bit of a information about the concept of simultaneity, or things happening at the same time. Right. Typically, if you and your friend are together, right, or even really close to each other, then you can say that two things that you witness happen at the same time, your friend will probably agree with you, right? So an example that I typically say is if I'm pointing at the board while I'm talking, right? Well, if you're sitting in a classroom and I'm in that same classroom and you're observing me, right? You would probably say that I'm pointing to the board while I'm talking. And so therefore, right, both of those events occur simultaneously. Now, obviously, I'm the one doing the pointing and talking, so I would probably also say that they occur at the same time to me. But once you start to get really far away from me, that's probably no longer going to be the case. At that point, right, then what's going to happen is you're going to actually have a little bit of a delay, right? My words would probably reach you a little bit slower than the visuals of me actually pointing at the board, right? And that's for a very simple reason, that being that light travels faster than sound, right? So if the distance between us is considerable, there will be a slight time delay between my actions and my words then too. That's something that actually has to be taken into account even if you're playing music in a really large venue, and you're really spread out, for example, if somebody's like really far back from the crowd, and somebody's a little bit closer, then typically they're supposed to actually kind of anticipate that delay a little bit. Now, nobody really thinks about that too much as far as I'm aware. But it is something that is noticeable, depending on the scenario and depending on how big the distance between you and the two events happening actually is. So, a good example of this as well, too, has to do with lightning and striking two ends of a train. So kind of a nice little picture, right, to go along with this. There's actually a really nice simulation online too. I don't actually remember what the actual URL for it is, but if I find it, I'll link it in the description for you guys, so you can kind of play around a little bit with it too. It's probably better than my drawing anyway. But in any case, right, imagine that there's somebody inside of a train, right? And then there's somebody, of course, not inside of the train, and lightning strikes both ends of the train at the same time, according to a person who is outside of the train. So it's going to hit both of the endpoints at the same time relative to the person outside of the train. Well, the person outside of the train is equal distant from both of them, so it makes sense that they should observe the two strikes hitting at the same time, right? That's an equal distance between both of the strikes and the person, right? And light moves at a constant speed, so that should happen at the same time. You would also say probably that the same thing happens to the observer inside of the train, right? Because both of these distances are approximately the same. Light again moves at the same speed, so that should take the same amount of time. But then, when you change the situation slightly, things become a little bit more complicated. What happens when when the train is moving, for example? So the train is moving, lightning strikes both ends as shown, right? Again, to a stationary observer at the same time. Well, which one's going to reach the observer first? Well, at this point now, when the lightning is traveling towards the observer has moved a little bit. So the train might be located here at some other moment. Well, at that point, right, the person is now located here, and because light travels the same speed, we'll notice now that since the person has moved from the red to the blue, the lightning strike on the left side of the train has a greater distance to actually travel. The lightning strike on the right side has a tiny distance to travel, which means that relative to that moving observer, it is actually the strike at the front of the train that would hit them first, or whichever direction the train is moving, whichever strike was in that direction. So that one should reach the observer first. Now, on a normal daily basis, are we really going to observe that? No, trains do not move fast enough for that to really happen. But you can imagine perhaps if you're moving really close to the speed of light, which is actually about what my drawing is representing here because of how much the train moved. I also didn't draw the train exactly the same size as before, but ignore that part. Right, but with how much the train moved before the strikes reached the person, that is a considerable speed that that train must have to ensure that the lightning strike on the right side doesn't have to travel far, and the one on the left has to travel really far. So but it's a nice sort of little thought experiment that kind of talks a little bit better about simultaneity and time dilation, right? Being that when you're perceiving two events to happen at the same time in one frame of reference, they might not be happening at the same period of time in a different frame of reference, right? So in other words, if you are starting a clock when you're stationary, starting a clock when you are moving, right? Well, both of those clocks might read different values when you are observing something. And so that is where the concept of time dilation comes into play. Now, to actually derive our formula for it, we have to do quite a bit of, not too much actually. It's pretty simple geometry, but the notation gets to be a little bit weird. So what I want you guys to imagine in order to derive our time dilation formula is imagine that we have a spaceship. And in that spaceship, you've got a light. And the vertical distance between the light and the other end of the train, we're going to call D. And I apologize if I'm going a little bit slow or kind of stuttering right now, too. I am actually looking at my notebook because I want to make sure that I'm using the correct notation and have the correct kind of equations here as well, too. But D is the actual vertical distance here. And so to somebody who's actually inside of the spaceship, well, what's the light going to do? It's just going to go straight up and come back down. So we can say that that period of time is going to be what we call delta t zero. So how much time is it going to take for that light to go up and back down? Well, light moves at a constant speed, so the time for the light to return back to the source should just be equal to its total distance traveled divided by the speed of light, or 2d over c then. So that's kind of nice. But if this spaceship is moving, right, which we typically say it is, we're going to give it some velocity u to the right without loss of any generality. Well, in that point, then, if you're observing this ship in the light from outside, that light's no longer going in a straight path because the source isn't located in the same spot. At a later point in time, the source might be located right here. So in order for the light to get back to the source, it actually does have to travel in a sort of triangular configuration. Now, you could reason through that both of these distances must be the same, the two diagonal dotted lines, and so we can make use of that to help us solve our problem. So what that kind of tells us then is that allows us to create two right triangles. So those two dotted lines, those are our two diagonals here. And then the horizontal line is how far the source actually moved. But then in addition to that, of course, we can bisect this, and now we have our two right triangles, one right here, one right here. Well, we already know a couple of things. We already know, for example, that this vertical, the height, is equal to d. We also know that the distance that the light source moves should be related to the velocity of the source relative to a stationary observer. So we could say, okay, well, if the entire time that it took the source to get from, say, point A to point B, we could say that that is referring to delta t, which is equal and I'm just going to write it out because I think that'll make it a little bit more clear and kind of give you something back to refer back to. But it's the time taken for the source to move from A to B in a stationary observer's frame, which makes sense because in the source's frame, the source doesn't move. Right. But if you're somebody outside of this moving ship and you're stationary, you're watching the ship move, you will see the source move. So in that sense, you could actually say, okay, well, what is this distance between A and this middle part right here? It should just be U delta T over 2 then. Because the entire distance to move from A to B is just U delta T. So you divide that by half, you get U delta T over 2. You could also say then that this diagonal side should be equal to C delta T over 2. What that refers to is the fact that the light is going up, coming back down, right? And so in other words, in your frame of reference, this delta t, you should have delta t is equal to the distance 2 times the length of this side of your triangle. Uh, what do I want to call that? I guess we'll call it h for hypotenuse, divided by c then. So you can solve that and you can get delta t. So delta t 0 is relative to an observer in the ship, relative to an observer in the ship, how long did it take that light to go up and come back down? Delta t, just no subscript, is the amount of time it took the light to go up and back down to return to the source, but from a stationary observer's point of view. Well, like right triangles, you can actually use Pythagorean theorem with all of the sides then. So what we have when we do that is you get c squared delta t squared over 4 equals d squared plus u squared delta t squared over 4. Well, you're probably wondering, okay, well, how is all of that going to help us? Well, we also know what d is in terms of delta t 0. We can solve this equation here. On the right side, you get d is c delta t 0 over 2. So plug that in for d inside of our Pythagorean theorem. So you'll notice that all of the 2's or the 2 squareds, aka the 4's, will cancel. So I'm going to get rid of those. So you're going to be left with c squared delta t squared equals c squared delta t 0 squared plus u delta t squared. Something that looks like this. I'm going to put all the delta t's inside parentheses just to make it a little bit nicer. So it looks something along the lines like this. Well, if we want to, the entire point of this is to figure out how are t and delta t actually related. Well, now we can actually do so. We can solve for one or we can solve for the other. Typically, time dilation is written with the solution of delta t equals stuff, so we're going to do the same thing here. So you get, sorry, this should be a u squared. So you get c squared minus u squared delta t squared is c squared delta t 0 squared. And then we can solve that. So I'm running a little bit out of space here. So I think I'm going to go ahead and erase my picture here just to keep the derivation all together. So I think that should be fine. The triangle is what's important now anyway. So if we solve that for delta t squared equals delta t 0 squared over C squared minus U squared all over C squared. So I've rewritten the C squared in the numerator on the right side as a denominator inside of a denominator because then I can simplify that a little bit into the form that we wanted at least. So delta t zero squared divided by 1 minus U squared over C squared. And that tells you then that delta t, the time for a stationary observer to witness this light moving, equals delta t zero over square root 1 minus u squared over c squared. And this, it's customary typically to say 1 over the square root is equal to something called gamma, which we typically just call the Lorentz factor. So that actually tells you now that, okay, well, if I have something that's moving, it is actually going to read a smaller time. The clock in that moving frame of reference is going to read a smaller time than the clock for the stationary observer. Why? Well, if you plug in any velocity for u, or any speed for u rather, you are always going to get a gamma that is greater than 1. So the stationary clock should read a larger time than the moving clock. I'm going to go to the next slide now because all of that is, not all of that, but the equation is typed out here. And you can see exactly how it looks. It's exactly the same thing that we just derived. Typically, delta t zero refers to what we call the proper time. That's a fancy way of saying again that it's the time measured by an observer moving, right? So delta t is by a stationary observer, and delta t zero is by the moving observer. So let's go ahead and actually see an example as to how we can use that question. So you have an asteroid which is flying past the Earth at a speed of 0.1 c relative to the Earth. So here's the Earth, right? That's our stationary observer. And then you've got your asteroid. We're sticking with 1D, so we'll say that U is equal to 0.1 c here. This is our asteroid, so E and A. The question that we have then is an observer on the Earth observes that the asteroid travels 1 times 10 to the sixth meter, so a million meters. That's our distance, right? Delta x. The question that we have, how long does this take to an observer on the Earth, and what about in the frame of reference of the asteroid? Well, you could say that, okay, well, the asteroid doesn't see itself moving, so it should take 0 time. That doesn't really give us a satisfactory answer, though, right? So we want to solve for how long it takes for an observer on the Earth, and then use time dilation to figure out how long it actually took in the frame of reference for the asteroid. Lucky for us, we've got both distance and time from the Earth's perspective. Distance and speed from the Earth's perspective. Distance and speed are both given to us. We can solve that for time just by dividing those two numbers. Since the velocity is 0.1 c, you will notice that I actually plugged in zero point 0.1 times the actual c value because I wanted to get a numerical answer for delta t. So this is what delta t would be in our equations. Is it would be 0.0333 seconds. I went as far out as I could. I know that we're not really following significant figures here, but it's because I want you to see what delta t zero is and compare it to delta t. And if I don't go out to this many figures or this many digits, you're not going to see a difference. So yeah. So to figure out what delta t zero is, right? We already know the time in the stationary frame, that's delta t. We know u is 0.1 c, the c's cancel, so we can just say 1 minus 0.1 squared in the denominator, and you can solve all of that for t0 then. So if you solve for t0, right, you have 0.0333 equals t0 over the square root. Solve that for t0. That is what you end with for delta t0. Notice how small of a difference it is. It's 0.0002 seconds different from the clock on Earth. So quite a small difference there, right? But you can imagine that as something is going really close to the speed of light, that gamma factor is going to really rapidly diverge. It's really rapidly going to become a really high number. And that will actually cause the time difference to be extremely significant. So, you know, zero point 0.1 C, a tenth of the speed of light, you're not really going to notice that big a difference across a million meters. But, you know, if you were to do this across, say, like a trillion meters, then obviously you would have to multiply all of this by like a nice, lovely factor of a million, and you would definitely see a big difference there. Right. Again, if you're moving really fast, if the asteroid is moving really fast, rather, really close to the speed of light, like zero point 0.7 C, then you're going to have a much bigger difference in what your two clocks are actually measuring as well. So it's kind of a neat sort of topic. Yeah, but it's a nice sort of example to see how exactly moving clocks move slower, right? You can see that even at 0.1 C, the difference is kind of small across a very small different distance. Right, but again, if you travel for a longer distance or faster, you're definitely going to notice a bigger difference there. But it does tell us then that moving clocks and stationary clocks do not read the same time. They don't observe an event taking the same amount of time from two different points of view then. So that's it for today. That's it for time dilation. Next video, we get to talk about length contraction, which talks a little bit about how the distances will actually change as things are moving really fast near the speed of light. So thanks for watching, guys, and I'll see you on the next video.